0 factorial is equal to 1, and here's why. So the question of 0 factorial is kind of tricky because of how factorials work. So for example, 2 factorial would be notated like this with an exclamation point, or exclamation mark, which would be all the natural numbers starting at 1 and going up to your selected number, which in this case is 2, multiplied together. So it'd be 2 times 1, which is just 2. So if it's 4, you get 4 times 3 times 2 times 1, and so you get 24, and for 3 factorial, you'd get 6. But that's kind of an issue when you introduce 0 as your selected number, because the lowest number in all of these sequences is always 1. So when you add 0, it becomes kind of a problem. The purpose of this claim is to get around that problem. The first step is to just create a list of all the natural numbers ascending. So starting at 1, 2, 3, 4, 5, 6, all the way up until infinity. And the second step is to raise every single one of those numbers to the power of n. And n can be any number. So, for example, let's say n is 3. So we'll do all of these numbers to the power of 3. And you would end up with 1, 8, 27, 64, 125, 216, and 343, and then so on, of course. So let's stick with this series of numbers as an example. Step 3 is probably the most confusing. It's to do the following process n number of times, which is why n has to be a whole number for this proof, because in order to do an action, you have to do that action a whole number of times. And so the action is to find the difference between every pair of adjacent terms. And so you'd find the difference between 1 and 8, right? And so you'd get 7. And you'd continue to do that between every single adjacent pair. And then what you're left with, I'll just go ahead and fill them in here. Is another series of numbers. But it also says to do this action n number of times. And so we've done it once, now we need to do it 2 more times, since n is 3. And so I'll go ahead and fill these numbers in. Again, we're just taking the difference between every adjacent number. And so the difference between these two would be 12, and these two would be 18, and so on. And then finally, you get a series of numbers where all of the numbers are exactly the same, and this would be your result. So, when n is equal to 3, the result of the function is 6. I went ahead and did the results for all the other 4 numbers of the first 5 counting numbers, so 1, 2, 4, and 5, and the work is right here, and it kind of took a while, but hopefully you see the pattern here. I've laid them all out here, that the results are always n factorial, where 1 is equal to 1, 2 is equal to 2, and then the result from n equals 3 is 6, because 3 factorial is 6, 4 to 24, 5 to 120, and that pattern continues forever. So now, what happens if we plug in 0 for n? Well, let's put n as 0, and we put 0 as the exponent for all of these, which, as you know, would just be, well, 1, because anything to the power of 0 is just 1. You get a series of 1s, and so on, all the way until, well, just an infinite series of 1s, I guess. But remember, up here it says to do the following function n number of times, and since n is 0, then we don't do the function at all, and this is our final sequence. The resulting numbers are all the same, and so the result is 1. And since the result is 1, and n is 0, and n factorial must be the result, that means 0 factorial must be equal to 1.